then we shall. Yeah. So today our topic is going to be non-abelian gauge theory.
Yang-Mills.
Yes. Um, or Yang-Mills theory. And you may have heard that, unfortunately, Yang passed away a few days ago. Okay. I believe that you have also had classes on abelian gauge theory. And the non-abelian version is just going to be a slight generalization of that. Um, we will need a little bit of Lie algebra theory, which I believe you may have encountered at the beginning of this course. We will not need much, and I will, instead of trying to review a lot of theory at the same time, I will try to give the necessary results as we go along. But we do need a little bit of reminder at the very beginning. So I'm going to assume that all of you have some familiarity with the definition of a Lie group and the associated Lie algebra. So let's say, so G will be a Lie group. Throughout this talk, I will mostly use notations appropriate for unitary Lie groups. So it will be something like UN. But everything I will say applies basically in a straightforward manner to also SO. Yeah, any kind of SO, or okay, or has slightly more things. Anyway, so you can take them to be unitary or orthogonal. Always also fine. It can also apply to the symplectic group, but it may require a little bit more generalization. And then there are also some other Lie groups, which I will not talk about. And these so-called exceptional Lie groups. You can assume UN to be the group of matrices that are unitary. Let's say N by N matrices. N by N matrices are unitary with complex entries. This, as a working definition, is fine, but you should keep in mind that a group is an abstract object. It doesn't necessarily have to be defined using matrices. But whatever the abstract definition may be, it is going to be isomorphic to this group of N by N unitary matrices. So for now, let me just use an isomorphism notation. And associated to any Lie group, you have a Lie algebra, which is usually written with a small letter, UN. And this is going to be isomorphic to the Lie algebra of N by N Hermitian matrices, traceless Hermitian matrices. Well, if I keep you, okay. The traceless part comes from special Hermitian. And if we just say Hermitian, it's unitary. I may sometimes assume that it's a special unitary. Um, Another thing that we need, um, let's also recap some properties of Lie algebra. So a Lie algebra is basically a vector space, uh, a vector space V with a bilinear map called the Lie bracket. So basically what it does is that you can take any two elements, one from each copy of your vector space, and then map that to another element of the vector space, um, something else in the vector space. And this operation has to satisfy certain properties. So for example, it has to be antisymmetric, and it has to satisfy something called the Jacobi identity, which looks like the following. So given for any three elements of your Lie algebra, this has to vanish. So this is called Jacobi identity. Um, Here, this notation can be a bit confusing because it does not necessarily mean what you know as commutator of matrices. And this gets a bit confusing because we often use, implicitly at least, that by UN we have a Lie algebra of matrices. And if you define UN as a Lie algebra of matrices, then this operation is nothing but the commutator of matrices. But in general, in an abstract definition of Lie algebra, this operation doesn't have anything to do with matrices or commutator. But unfortunately, they have the same notation. Hopefully, this will not cause a huge confusion. But if there is any confusion, please ask. If you need to clarify whether I mean commutator or just the abstract Lie bracket, please ask. Here I just mean the abstract Lie bracket. Um, this will all be true for matrices. Now, this relation, I'm sure you have seen before, but if you are seeing this for the first time, it may seem a little strange. Why, out of all the things that I could have written down, why this one? This actually follows from something more familiar to us, perhaps. So as I was saying, that a Lie algebra can be associated to a Lie group sometimes. In this case, yes. And the correspondence goes as follows. So for an element in the Lie algebra, let's say we're talking about UN, um, you have an element of the Lie group given by something called the exponential map. And again, the notation is such that it will look like the usual e to the power something something. And if you are actually using matrices, that is indeed the case. But in general, that's not, it doesn't have to be like that exactly. But in any case, let me just write expx for the moment. So it's some kind of map that gives you an element of the group. And in a group, we always assume that the group multiplication is associative. So if you have three elements, X, Y, Z, capital letters, of your group, then when we multiply them, we assume that the multiplication can be done in any order. I mean, you cannot commute things because it's the group elements do not necessarily commute. But whether you multiply this first and then you multiply this, or you multiply these two first and then you multiply this, that shouldn't matter. And this property, which is called associativity, which I'm sure you would agree that is more natural. This, when you bring it back to Lie algebra via this relation, which I'm not spelling out what this means abstractly because later I'm going to use the matrix notation. Uh, this associativity will translate to the Jacob identity. Okay, so Jacob identity is nothing but the statement that the Lie group associated to the Lie algebra is associated. So this is kind of the shadow of the associativity in the Lie algebra setting. Okay. These are some basic facts. And what we will need in writing down formulas for the non-abelian gauge theory, or really in most cases in physics, when you talk about Lie groups or Lie algebras, what we really need are representations of these things. So let us also recall a couple of definitions regarding the representations of a Lie group and a Lie algebra. Suppose G is our Lie group, then a representation mm, of G a representation of G is representation of G on a vector space. So let's say M is a vector space. So representation means a group homomorphism from G to the algebra of invertible matrices that act on this vector space. Okay. So so M is a vector space, and this is the group of invertible matrices acting on M. Okay. And any such homomorphism, maybe I should, what should I call it? Let's say R. R is a representation of this Lie group. Um, and associated to any representation of the Lie group, there is going to be a representation of the Lie algebra. Let's call it rho. So in mathematics, there are some standard notation for referring to the representation associated to the Lie algebra, which sometimes you will see some notations like this. But let us not use strange notations. I will just call it rho. This is going to be a homomorphism from the Lie algebra of G. So this notation means the Lie algebra associated to the Lie group to basically all the matrices. All matrices acting on M. Okay. And the space of all matrices acting on a vector space is a Lie algebra because there you can say that the Lie bracket is nothing but the matrix commutator, and it will automatically satisfy the Jacob identity. And any homomorphism from your Lie algebra into this matrix algebra is a representation of this Lie algebra. And so once you have a representation of the Lie algebra, so from there you can go back to the representation of the Lie group by the exponential map. And in this case, it is nothing but the exponential of a matrix. So here there are various conventions that we can take. So for unitary, so let us fix some conventions. For unitary group, our representations of the Lie algebra is going to be Hermitian for, let's say, for UN. Representations are Hermitian, meaning that elements of this Lie algebra would be represented by Hermitian matrices. And then, so if X is an element of this Lie algebra, then rho x is an element of GLM for vector space M, and rho x is Hermitian, meaning this, and from this we can construct a group element this exponential map, which we e to the power I rho x. Okay. And obviously, if rho x is Hermitian, then if you take the Hermitian conjugate of this, you will find the inverse. All right. If you take the dagger, it is nothing but e to the minus rho x, which is the inverse, i.e., this thing is unitary. So from a Hermitian matrix, you construct a unitary matrix. Okay. The last thing about Lie algebras that I can mention now is, so we will choose. Okay, so one caveat of this abstract versus matrix definition of a Lie algebra. Here, if you think of UN as the Lie algebra of n by n Hermitian matrices, then X is automatically a n by n Hermitian matrix for you. However, rho of X, we will always take it to Hermitian by convention, but it doesn't have to be n by n. It can have any dimension because the dimension depends on what m is, right? And that just depends on our choice of representation. So just keep in mind that elements of UN can be represented by matrices that are not n by n. Okay, right. Now, we will also often work in a particular basis. So meaning that our UN will have some kind of basis, UN with a basis. Let's say our basis vectors will be, we will denote them by TA, where A goes from 1 to n square. By the way, so n square is the dimension of UN. Yeah, I'm sure you can prove that. So we will choose some basis vectors, and once we have chosen some basis vectors, we can write down the equation as follows. So TA, TB, the Lie bracket. This is another element of the same Lie algebra. So we can write it in the same basis. And if we do that, so it will look something like the following. So F, we remember which two elements we took the commutator with. It's ABC and TC. Okay. And yeah, I'm using Einstein summation notation. Repeated index means summation. Okay. So if you know these numbers, then you basically know the Lie bracket, right? Because if I give you any two arbitrary elements of this Lie algebra, you can write them down using these basis vectors. You can then take the commutator and then apply this formula on the basis components, and you have the commutator of any two arbitrary elements. So these numbers define the Lie algebra. And these are called structure constants. But notice that they are basis dependent. So there are no unique structure constants associated with any Lie algebra. For example, instead of taking t, I could take t over 2 as my basis vectors, right? And then in order to keep this equation the same, you would put a half here. And then your structure constants are divided by half. So the structure constants are not unique. They depend on your choice of basis. But once you have chosen a basis, they become useful. Here, there's also a convention that we have to choose whether we want this to be real or complex, let's say. So if T is Hermitian, then their Lie bracket is under Hermitian, right? You take the dagger, then you take the dagger here, but you change the order. but this is antisymmetric, so that gives you an extra minus sign. Here, this doesn't do anything, you have an extra minus sign, right? So this becomes, so if I write it like this, then this becomes imaginary. So let us use the convention where the structure constants are real. So let us put an I here, and then the structure constants are real. Okay. Yeah, so there are many conventions. It's entirely possible that sometimes I will write something in a convention that's contradictory to another convention that I used earlier. Yeah, that's a problem. Okay. Um, Let me just introduce one more quantity associated to Lie algebra, which is a metric. Um, a Lie algebra has something called a Killing form. Which is a bilinear map. Um, and let's say that, okay, we will use kappa to denote this Killing form. So what it does is that it takes two elements of Lie algebra and gives you a real number. And it is linear. So in order to know what this is, you only need to know how it acts on the basis vectors. And so this we will write as KAB, kappa AB. So kappa AB will basically act as a metric tensor on the Lie algebra. So whenever you have Lie algebra indices AB, you can raise or lower them using this matrix. Um, uh, just since I'm using a matrix, let me use a metric. Let me be slightly more careful, and let's say that we use contraction only between upper and lower indices. This, of course, would not matter if this were the delta function, right? And for un, we can actually normalize our basis vector such that this is delta function, Kronecker delta. And in that case, it doesn't matter whether indices are lower or upper, right? Because you're raising or lowering them with delta function, Kronecker delta. So it's the same. And that's why you will often see that when people write indices for UN, they are not really maintaining this upper lower index distinction. And actually, eventually, we will also do the same. So note that this can be normalized to Kronecker delta. All right. So now that we have remembered some formulas from the algebra, let us get to physics. Okay. So we will use some of these formulas. Probably not so much the metric, except for a few cases. All right. Okay, so let us recall our notion of symmetry. So we have talked about scalar field theory. We briefly mentioned fermions, and you have by now seen abelian gauge theory as well. So you have encountered spin 0, half, and spin 1 fields. But to begin with, let us focus on the simplest case of spin 0 fields, so meaning scalars. And a theory of scalars is defined by its action functional, and a free theory is defined by the kinetic term, which in four dimension looks something like the following. Let us assume that the scalar is complex. Then you have something like this. And if you have an interacting theory, then you also have interaction terms, where so far it can be anything, any function of phi. So one example that we have considered before is where this was just phi cube. This is a bit problematic in this case because well, if I write just if phi is complex, then I cannot just write phi cube. I also have to write something like this at least, so that the action is real. On the other hand, if I have phi to the power 4, then I can generalize that to complex scalars in a different way. I can say that I have phi star phi squared. Right? This is real and also quartic. So this also works. But you could have also, of course, written phi to the power 4 plus phi star to the power 4. That would have also been real. But for now, let us choose this one because if we choose this kind of interaction, or slightly more generally, if I write here any function of phi star phi, which can be square of this or what have you, then this action has a particular symmetry. So what is the symmetry? You can transform phi to be, you can multiply phi by any phase. So let's say e to the power I alpha. Then its complex conjugate gets transformed as e to the power minus I alpha. Um, and their product is invariant. Okay. Um, Now, if I transform my field as follows, this action does not change at all, right? Because it is always a multiplication between um, a field and its conjugate. And this is a function of this product, which is invariant by itself. So as long as alpha is a constant, meaning it does not depend on x, so you have here e to the power I alpha, here you have e to the power minus I alpha, and they cancel each other. Of course, this doesn't work if alpha is a function of x, because you have derivative and you cannot commute a function and a derivative. And you saw in case of the Lebesgue theory how to tackle that problem. Right? Now you have to modify the derivative so that you can force it to be invariant under a space-time dependent transformation like this by adding something to the action. Okay, so our goal is to generalize that idea when this transformation is not just a phase, but more complicated. But in order to see that, we need more than one field. So let us introduce, let's say, n fields. So phi 1, phi 2, dot, dot, phi n. So we have n complex scalar fields. Okay. With this, we can write down an action as follows. This is a straightforward generalization of this. So basically, I have added n copies of this kinetic term, one for each type of field, 1 to n. So there are n of these things. And this is not just a sum of n copies of this potential, but rather it's the same function, but now it's a function of the sum of the norms of each of the fields. So here you have now many more terms, terms involving products of different copies of phi. That's okay. But now notice that, well, okay, it's going to be better for us if we try to use a better notation. So let us define by phi a column vector that contains all of the fields. So it's a column vector with n rows. And by phi dagger, we will mean the row vector, which contains all the complex conjugates. And then this can be written in a slightly more compact notation. Okay. All right. So now we can see that we can directly generalize this when alpha is coordinate independent. So let's say that phi goes to phi prime, where phi prime is a unitary matrix times phi. So here U is an n by n unitary matrix. So in components, so phi prime I is nothing but summation over ij phi j. Okay. So we have some new fields which are just linear combinations of our old fields, but the coefficients are coming from unitary matrix. But now you can see that if you write down the same action using this new field phi prime, it's the same as the old action for the same reason as in the U1 case, because phi prime dagger delta square m square phi prime is nothing but phi dagger u dagger, your operator, and then u phi. But again, when u does not depend on the coordinates, it doesn't matter that this is a derivative. You can just commute past these things. And since u is unitary, u dagger and u cancel, and you are left with the usual kinetic term for phi. And the interaction part is manifestly invariant, right? Because phi dagger phi is an invariant of unitary transformations. So you would get u dagger u, phi dagger phi, and they will cancel. Okay, so what that means is that the action written in terms of the old field is the same as the action written in terms of the new field. So this is a symmetry. So this transformation is a symmetry of this action. Very well. But now let's try to mimic what you did in the abelian case. So what happens if you take U to be space-time dependent? Right. So then you cannot commute past this derivative anymore. But before you try to modify the action and try to force it to invariant by doing something to it, you may ask why you would want to do this at all. Right. This transformation is already a symmetry of this action. So what do you gain by promoting this to be space-time dependent? I mean, what is the physical motivation for us to want an action that would be invariant under a transformation like this with space-time dependent U? And the motivation is not just that you are discovering some new kind of symmetry or anything like that. And to be fair, the motivation is not entirely obvious at this stage. What you will find later, though, is that you can write down some relatively simple action which has a symmetry involving space-time dependent transformation that is equivalent to a theory that doesn't have any such symmetry, but that theory is very, very complicated. So I will not give an example at this moment, so I will also not spend too much time on it. But one motivation for considering space-time dependent symmetry is that some theory some simple theory that has a space-time dependent symmetry, or in other words, gauge symmetry. And we will explicitly write down example of a simple theory with gauge symmetry, so you will see what that looks like, non-abelian gauge symmetry. But you will often find that such a theory is equivalent to a some complicated theory without nothing else. Some complicated theory without gate symmetry. Or maybe I should explicitly write without gate symmetry. Okay. And you will often find that this theory is so complicated that you cannot even write down Lagrangian for it. Whereas this theory is simple enough that you can write down Lagrangian and do quadratic computations here. But at the end of the day, you can directly translate your computations here to this theory. So this theory will have some elaborate definitions because you cannot write down Lagrangian, and this may be very difficult to do computations in. So the motivation that I'm giving you right now for considering gate symmetry is that even though it will seem like we have something simple and then we are making it more complicated, and in this example, that is true. We have started with something that is extremely simple, and then we will force it to be gauge invariant by making it slightly more complicated. This tool will allow us to discuss theories that are even more complicated, so complicated that we cannot write down Lagrangian. Okay. Yeah, so it's something to hope for in the future. But for now, let us see how we can write down a theory with non-abelian gauge symmetry. And the process is basically identical to what you did in the abelian case. So this should look very familiar to you. Yeah. So let us try to see how we do this. So basically, I mean, just notice that the main problematic term in this Lagrangian that prevents it from being invariant under a space-time dependent transformation right now is really just this derivative term. So if we want to fix this problem, we have to do something to the derivatives. Everything else is automatically already invariant under space-time dependent transformations, right? This term or the m squared term, these are fine. Okay, so let's focus on the term that is not invariant at the moment, which is phi dagger, derivatives, and phi. Okay. Any questions so far? If you have any question, you can of course write in chat. You can also just ask. All right.
You can think of some applications in dualities where
Of gauge symmetry?
yeah, no, we have this simple model, and then we can just go into do a duality and explain the complicated thing with this simple theory with the gauge symmetry.
Yeah, indeed. Yes, exactly. So that is what I have in mind. That there are various dualities in quantum field theories that tell you that certain theory is equivalent to certain other theory, even though they have different formulations. Meaning, so once you map the observables in the two theories in an appropriate way, their correlation functions or expectation values become the same.
Right.
And this equivalence that I mentioned, it is precisely an example of such a duality. I mean, when you see an example, this will be an example of a duality, where on one side you will have a gauge theory with a simple kinetic term with some slightly modified covariant derivative and so on. But on the other side of the duality, you will have a theory that doesn't have any gauge symmetry. So in that sense, maybe you can call it simpler, but that theory will have such complicated interactions that it will essentially be impossible for us to write down Lagrangian. Exactly. So then you can use this kind of description to describe both sides, basically.
Yeah, got it. Thank you.
Okay. So the term that was preventing us from having a gauge invariant action was this one. Now, okay, so what is the transformation that we want this to be invariant under? It's that we want phi x going to phi prime x, which is some unitary matrix, but now depends on x times phi x. Okay. All right. And so let me first write down the answer, how to modify this Lagrangian, and then let me prove that it works. So the modification that we're going to do is that we are going to replace the partial derivative with the covariant derivative. And it will even look like the covariant derivative in the abelian case. So it's just the partial derivative minus I, some number which can be anything. And then we have to introduce a new field that carries an index corresponding to your spacetime coordinate. So this is a Lorentz vector. In other words, this is a spin 1 representation of your Lorentz symmetry, or a spin 1 field. Now, the difference from the abelian case is that in the abelian case, you introduce some field like this. So it's just so for each index, it's just one field. But now, for each index mu, we have to introduce, assuming that this is unitary, we have to introduce n square fields. So we need another index A, and then we need remember that we have chosen a basis vectors TA for our Lie algebra UN. So we need that basis vector. And we need another thing, which is a representation. So some representation rho of this thing. And what this representation is depends on how these things transform under a unitary transformation. So let me try to disentangle some of the notations. So what we are saying is that we have a field phi, or rather we have n fields, phi 1 to phi n, put inside this column vector. And we want to view this column vector as a representation of un. So remember that a representation of un is a homomorphism from un to the group of invertible matrices that act on some vector space. Now, in this case, this vector space has to be the vector space where phi belongs. Now, phi was a column vector with n rows. So, as you can see, this belongs to Cn, right? At a fixed location, at a fixed x, this belongs to Cn. So M in this case is Cn. And if you represent elements of Un as unitary matrices acting on Cn, they are again just n by n unitary matrices. So in this case, this representation is trivial, or really just the identity, in the sense that on this side you have n by n unitary matrices. On this side, you also have n by n unitary matrices. So you are not changing the matrices themselves. You are just taking these matrices and calling them the representation. And the simplicity may cause some confusion down the road, unfortunately. But try to keep in mind that there are basically two things. One is the group itself, and another is the representation. But in this case, both happen to be exactly the same thing. And so this representation is basically the representation associated to this representation, but acting on the Lie algebra. In other words, these row of TA, these are also going to be So recall that associated to a representation of the group, you have a representation of the Lie algebra acting on basically all matrices, acting on the same vector space. So you're mapping to the space of matrices acting on the same vector space. So rho of TA is again just an n by n Hermitian matrix. Okay. All right. So these are detours. So I was explaining how to modify the partial derivative in the non-abelian case. So it's basically the same as abelian case, but you have an extra index, and which is contracted with a representation of your Lie algebra basis vectors. And how many of the things you need, of course, depends on how many basis vectors you have, which in turn depends on what group you want to transform your field with, because it's the Lie algebra of that group. Okay. All right. Now, so I claim that if you just replace the partial derivatives in here with this covariant derivative, and in addition to this modification, you have to specify how this new field transforms when you do a transformation over fields. So you already know how phi transforms. Because we have introduced a new field, we also have to stipulate how this new field transforms. So let us now stipulate that. A mu AX I'm going to use a slightly different notation. Let me define. So I will write this just as rho of A mu. Okay. There's some overlay. So if I just write A mu without this Lie algebra index, then it is implicit that I have summed over this Lie algebra index with these basis vectors. Okay. Now, A mu goes to, let's write X. A mu X goes to mu prime X, which is okay. Now, this equation, I'm here being a little inconsistent because this, because this A does not appear directly in this action. What appears is A multiplied by the representation of TA, which we are calling representation of A. So I should really put the representation of A. But again, recall that in this particular case, where we have n copies of these fields, this is trivial, this representation trivial in the sense that you are just taking n by n unitary matrices and representing them by themselves as n by n unitary matrices. And similarly here, you're taking n by n Hermitian matrices and representing them by themselves by n Hermitian matrices. So rho here doesn't do anything. TA is already an n by n Hermitian matrix, so we don't have to change it. We don't have to represent it by something else. It is representing itself. And because of this reason, in textbooks and also I will often omit these explicit reference to the representation and just write mu goes to something something. Okay. I am repeating this because this is only true when you have exactly n copies of this field and your group is also un. There are physically important examples, hopefully we will encounter some of them, where the group will be, say, un, and you will have a different number of fields. Let's say phi 1 to some other number m, where m and n are different. And in that case, you will have to remember to keep writing this row, because otherwise it will not make any sense. Right? If you put an n by n Hermitian matrix here, that cannot act on a column vector of length n. But for this example, we can omit these representations. Okay, so I have specified how to transform this new field. But just to be clear, let us also be very specific about what we mean by this modification, or how this new derivative acts on our field phi. So when we just have a partial derivative, when it acts on phi, what we mean is just that you act component-wise, right? So phi 1, del mu phi 2, dot, 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 del mu phi n. But when we write d mu phi, what we mean is that, so of course, the first term is nothing but this. The second term is, also, there are various conventions regarding the sign. You could take it to be plus if you want. And also, this I is tied to our convention of having these things as Hermitian. We could have also taken this to be anti-Hermitian, in which case you would not have this I here. So there are many conventions, and different sources will use different notations. Just pick one and be consistent. So now you have I, G, A mu A, rho T A phi. So what's going on here is that, so this part is nothing but this. And these are just numbers, right? So A mu A is just a number at a particular location. But this is a matrix, an n by n Hermitian matrix. And this is an n by 1 column vector. So this is a matrix multiplication. These are numbers, C numbers. N by n Hermitian. N by 1 column. And overall, this is matrix multiplication. Matrix times vector. Okay, so I'm just breaking down the components of this equation. And this is the result is a column vector, this is a column vector, this is a column vector. So that's how you evaluate the action of a covariant derivative, a non-abelian covariant derivative on a multi-component field. All right, so now let's check that if we transform our field like this, and if we transform our new field like this, then this action is indeed invariant once we replace the partial derivative with covariant derivative. There's actually nothing but algebra, so maybe I don't need to do the whole thing, but let's maybe do in parts. Let's see. Okay, so let's check something. So what happens to this Lagrangian if we do the coordinate transform, if we do the symmetry transformation? So you get phi dagger u. So everything depends on x. I'm not writing it every time, but just keep in mind that everything depends on x. Then you have dagger, phi, and then this. Um, Now you could write this as these brackets are very important, right? So you have to remember to take derivative over everything that appears afterward. So here all I've done is that I've inserted this in between the two derivatives. And this, of course, is 1 because u is unitary. So I haven't done anything. Now, so the main point is that if you could replace this with this and this part with this, then you would have the same thing that you started with, right? You would have the same thing. But you cannot do this. When u depends on coordinates, this operator is not the same as the partial derivative. It's the partial derivative plus some terms that depend on derivatives of u. However, let us just check that the covariant derivative has the property. And okay, I'm also ignoring to write the spacetime indices. Yeah, let us check that the covariant derivative that we defined has the property that u dagger covariant derivative of something, phi. This is the same as just the covariant derivative of phi. Because if you can show that this holds, then first of all, you can just replace this by del mu phi. I mean, of course, you cannot do this with del. We have to do it. You can do it with d. So you can replace this with d mu phi, and then applying this again, you can replace. You can replace this with d mu phi, and that would have been the same thing that we started with. All right. So let's see if this is true. Um, so this is our d mu. So we are doing two transformations at the same time. So we are changing our phi by this u's, which introduces this u and this u dagger. Remember that this comes from this equation, so where we had this u dagger. But you also have to simultaneously change a to the new field, right? So let us call that a prime. So we want to check whether this is the same as just d mu phi. Okay. Let's focus on the derivative first. All right. This term is the source of all our problems when this acts on U. Let's look at the other term. Okay. So here, the things that are matrices are U dagger, row, and this U, and this is a column vector. Now we need to substitute this definition of A prime. So in order to use this formula, so let us recall that we find a shorthand where when we sum over A, we just omit the index altogether. So this is row A prime mu. And this formula was for row A prime nu. So I think that's it. And then you have this part. Okay, now let's simplify. This cancels. This cancel. And this cancels. This cancels. Okay. So from the two i's, you have one. The g cancels. Okay, so from the first term, you just have row of A mu phi. Sorry. In the first term, we also have I, G, and everything. In the second term, we have plus. Okay, you have this. Now we are going to do an integration by parts. So recall that this term will, so when you put everything inside an action, so all of this will appear under an integration sign, right? So there will be a d for x. And under an integration sign, we can do an integration by parts with respect to this derivative. See. Okay, so here I'm actually skipping some steps. But after I do some integration by parts and cancel some boundary terms, you will be left with something like this. Okay. There's a little bit of skip here. But the point is, so once you have done all of these calculations, you find that this term cancels this additional term that came from transforming this derivative. So if you consider the sum of these and this term, so then what you have is simply this plus this, which is nothing but yeah, so recall that it's just partial derivative minus ig rho A, which is the same as partial derivative minus ig rho A. So what we have shown is that u dagger d mu u whatever it acts on, this is invariant under a transformation, under a space-time dependent transformation. This is the same as d mu, whatever it was acting on. Okay. And this is the key property of the covariant derivative, which I'm sure you have seen in the abelian case as well. And this property remains exactly true in the non-abelian case as well. And this leads to the invariance of this. So here, using this, you can replace all of these things. So phi dagger d square phi is it goes to phi dagger d square phi transformations. These things. And this. Okay, I'm not going to write this again. It's a bit long. Okay, so under these transformations, which we will call gauge transformations, this kinetic term is invariant. And the rest of the action that we wrote down was already invariant, right? So this m squared term and this potential term, they were already invariant. So now, from this computation, what we have learned is that in order to make the action for the free scalar invariant under a spacetime dependent unitary transformation of fields, we simply have to replace the partial derivative with the covariant derivative that we wrote down. Okay. So this is the first step in constructing a gauge invariant theory. So since this is an important step, let me take a brief pause here, and if you have any question, I can answer them. But so I will be back in 5 minutes, and then I will answer your questions. All right. If you have any question, you can write down in chat.
Well, the factor of phi should be on the first term when the last calculation was done, like below this line. Yeah, yeah, right next to Amy Weapon.
Here?
Yeah, the first term should have a phi, right?
This one. Let's see. Yes, of course. Phi. Thank you. Okay. Was anyone else having a bit of a lag? Is that still happening? So right now it seems to be all right. Yeah, unfortunately, the internet at my home is not great. And of course, it's a bit late, so I can't be at my office. Right. So there are no more questions. Or if you have any question, you can ask now. Okay, if not, then let's move on. So far we have constructed a classical action that is invariant under a gauge transformation by adding an additional field A and defining how that A should transform when we do a gauge transformation of our field phi. this does not tell you anything about the quantum theory, right? So what I mean by the quantum theory is that if you have a classical action S of phi, then you write down a partition function uh, by doing a path integration over your field configuration, right? So far, what we have done is that we started with some classical action that only depends on phi. We modified it to a new action that depends on phi and a vector field A, which also carries the algebra index. And we showed that this has a certain symmetry property. Okay, but so what about this path integration? In addition to doing this change, what do we do to this path integral? Well, if you don't do anything, if you simply leave it as S phi A, that is a perfectly valid thing to do, but it does not define a gauge theory in the sense that A is not a dynamical field. But what does it mean then to write down this theory? So this theory, once you have integrated phi out, the partition function, it will be a function of A, right? Because you have not integrated over A. You have introduced A in the action. So it is some fixed field. And at the end of the day, your partition function will depend on this fixed field. And so a field like this, which appears in the action, but that's something that you do not integrate over, is called a background field. So what you have done here is that you have taken a theory that has a global UN symmetry, and you have coupled that theory to a background U1 connection or a background U1 gauge field. Okay. And that is something you can always do. Assuming some subtleties referred to as anomalies do not exist. Okay, but now, if you want to write down a gauge theory, and
I'm sorry,
a gauge
can
theory,
you repeat that? You just said anomalies that don't exist.
Right, so I'm saying that when you can couple a theory that has a global symmetry to a background gauge field, you can do that when you don't have anomalies.
Okay, got it.
Mhm.
Thank you.
Yeah, no problem. Now, so as I was saying, that this does not define a gauge theory, because a gauge theory is defined as a theory where you have a dynamical gauge field. And dynamical means that you have to do a path integration over that field as well. So in other words, if you want to define a gauge theory, then you also have to integrate over A. Something like this. Of course, this is a very different theory from the one that we started with, right? This one. I mean, there is very little relation between, okay, I mean, there are obviously some relations, but it's not that this is some slightly different version of this theory. No, it's a completely different theory. This is a theory which has a global symmetry and has some field phi. And this is a theory that also has the same field phi, but it has a gauge symmetry and it has a dynamical gauge field. And this theory may be dual to some other theory that has a completely different description, where you don't have these fields phi, but you have some other fields. But let's say that for whatever reason you are interested in this theory. So you are interested in a theory of dynamical gauge fields coupled to some other fields with some global symmetry. Then you have to figure out a way to do this integration. And this integration, unlike this one, is more problematic. I mean, this integration can itself be problematic. because it's an infinite dimensional path integration. But this integration is problematic for a host of new reasons. So let us take a closer look at the integration
Can I
over
ask
the
a
gauge
question?
field. Yes, please.
So you're saying if we don't integrate the A variable, the A field does not have any dynamics?
That's right.
So why is that? Can you explain that a bit further, please?
Well, actually, you can kind of take it as a definition of dynamics, but in a slightly more intuitive and less precise term. So by dynamics, I mean that so a field has dynamics if it can propagate in some sense, meaning that you can compute correlation functions involving that field as an operator. So an operator is like a local operator is like a local excitation or a perturbation of some field. And if you can compute a non-trivial correlation function between two local operators separated in space-time, then that means that the local perturbation that you created at one location can propagate through space-time and then interact with some other perturbation or something like that. Now, you can only compute correlation functions of operators involving a field if that field appears inside the path integral, right? Otherwise, there are no operators involving this A field at the moment. There are operators involving the phi field. You can insert something like, well, this is the wrong line. Okay. Here, for example, you can insert something like this, and this non-trivially changes the path integral, right? Because you have modified the integrand by inserting something that depends on the variable of integration. On the other hand, if you add a field that you do not integrate over, then it's just, how should I say? I mean, if you think in terms of a finite dimensional integration, so maybe you're integrating something that has some parameters. So that parameter is not integrated over. So your ultimate result depends on that parameter. But you cannot modify the integrand in any way that affects that integration by inserting some function of the parameter. So there are no non-trivial correlation functions. So that's what I mean by not having dynamics. That there are no non-trivial correlation functions.
So in that case, A would just be like a classical source when we're not integrating
Exactly. Yeah.
it.
I mean, even if you insert some function of A inside the path integral, right? It just acts as multiplication by a number. It doesn't change the result of the integration other than an overall multiplication by something. Okay. So now let us promote A to a dynamical field by doing a path integration over it. And let us take a closer look at what's going on in this integration. But okay, so the first thing that you notice is that in order to do an integration over a field and for that integration to make sense, that field should have a kinetic term. Because if you remember how we computed the partition function for a field theory, the kinetic term provided the quadratic weight against which we could do a Gaussian integration. If you modify, if you simply modify the kinetic term for phi, so actually, I'm looking at the video from my computer, and I think there's again a lag between my iPad and what you can see. How bad is it? Okay, that's pretty bad.
There's a 5-second lag.
Yeah, that's pretty bad. But I'm also afraid of resetting the connection because the last time, well, the time before the last time, I didn't even connect.
We're three quarters through the lecture, so
Yeah. I think we just have to move on.
yeah.
Okay, so if you simply replace the partial derivative to a covariant derivative in the kinetic term for phi, then you have not added any kinetic term for the gauge field itself. So let us try to figure out how we can add a kinetic term for the gauge field. So the first problem with the gauge field is that it does not transform covariantly, meaning that so phi transforms relatively nicely. It transforms u goes to u phi. So it transforms as a representation of un. The field A, on the other hand, so A mu A, or perhaps we want to sum over the Lie algebra index and call it just rho A mu. This does not, this does not transform as follows. This is not the transformation of A, right? This is one term in the transformation of A. So if you see, so what happens to rho A? It goes to rho A prime, which starts with this term, which is what I would call the covariant transformation. But then it has this other term that has nothing to do with A itself, but rather it depends on the parameter of the transformations and derivatives and so on. So this is the term that's strange, meaning it's a non-tensorial term. Now we know how to write down invariant action when we have fields that are tensorial, right? Because so tensorial means that it has some, okay, roughly speaking, it means that it has some indices corresponding to some kind of symmetric transformation. So as long as you can contract those indices, you can cook up an invariant. But if something doesn't transform like a tensor, then it's not obvious how to make an invariant out of that thing. Well, so what that means is that we cannot directly use A. I mean, you cannot just say that, okay, so write down a quadratic term involving A. Well, we could do that. So you could write down A mu A. This is something quadratic in A. But you cannot use this. So, I mean, this term is not gauge invariant. If I do a gauge transformation, this will not transform into itself. It will transform into itself plus additional terms involving derivatives of u. So this is out. For similar reason, we cannot use things like a mu, a nu, a, and square of that. So by square of that, I mean that you take a mu again, a nu, a, right? You could have guessed something like this for the kinetic term for a, mimicking the kinetic term for the scalar, right? The scalar has the kinetic term del mu phi, del mu phi. You could also bring it here by an integration by parts, but this is one valid way of writing a kinetic term for a scalar field. But this would not work for A because A does not transform like a tensor. What would work? Actually, so for in the abelian case, this is what I think you wrote down, right? You would just write this and just contract the indices. Well, you have to antisymmetrize and then contract the indices. Yeah, but even that would not work in the non-abelian case. So let me write down what would work in the non-abelian case. So you have to define something called the field strength tensor, or whatever, the name doesn't really matter. So let me write down the abelian formula first. If you have only one gauge field, meaning no Lie algebra index, then you would say, just take this. And then you would square this quantity. And this is invariant under a gauge transformation, an abelian gauge transformation. But when you have non-abelian gauge transformation, you have an A here, you have an A here, so you clearly have to put an A here. but you have to do slightly more. You have to write something like this. Sorry, this makes no sense. This. I think the correct signs are something like this. Actually, there shouldn't be any I. All right. I am not 100% sure about the sign. It may be minus, but okay, up to some signs. So I claim that this is the proper generalization of the field strength tensor that you wrote down in the abelian case. So this is the correct formula. Now, why this is the correct formula? So you have to justify this by checking whether F transforms covariantly. And by that, I mean, you have to take this object. So again, notice that this is just a number. So once you supply the values of the indices, this is just a number. But this object, once you specify values of mu and nu, this is an n by n matrix because this is an n by n matrix. So what you have to check is that this goes to okay, and using the same kind of convention, I will write this as rho f mu nu. Yeah. So this goes to this. Well, this will be an exercise. I mean, you just have to substitute the formula for how this transforms and then do some algebra. But the point is that if, assuming this is true, so what happens to the quadratic term? So this is a matrix. This is a matrix. In order to add something to the action, it has to be a scalar. So you can take a trace. And you can further simplify this. So again, so this is just a number. This is just a number. So we can take those out of the trace. Okay. Now remember that at the beginning, I said that associated to any Lie algebra, there's a metric. And the metric is used to contract indices of Lie algebras. And maybe you know this, and if not, you can look it up in any place where they discuss Lie algebras, that the trace of any two basis vectors in any representation is proportional to that metric. The proportionality factor will depend on in which representation you have taken the trace. That factor is not really important here, right? Because it's just an overall normalization. But the point is that, okay, so up to the normalization factor, this is the metric of your Lie algebra, and then Fa mu nu, Fb mu nu. Yeah, so this metric is simply contracting these two indices. So basically we have, so via this formula, we have constructed a quantity that is antisymmetric in its two spacetime indices, and it carries a Lie algebra index. And here you simply write down the invariant by contracting all of the indices as you would with any tensor, right? And the reason that you can do that is because this object transforms like a tensor. So as long as you contract all of its indices, the thing that you have is invariant. Okay. And of course, this is also quadratic in the derivative, right? Because f contains one derivative acting on your gauge field. So when you square this thing, you get terms that have two derivatives acting on two s. So that's the usual looking kinetic term for bosons. Of course, you get other things as well. So if you square this, so here you have two a's. So if you square these, then you will have terms where you will have four a's. And then from multiplying from the product of this and this, you will have term where three a's and the derivative acting on one of the a's and so on. And those will become interaction terms for the gauge field, right? And those are the things that were absent in the abelian case because this term was absent. So you only, in the abelian case, you only had the kinetic term. If you square this, you only get terms with two derivatives and two a's. Only kinetic terms, no interaction. So we will, of course, take a look at the interactions more carefully. But for now, all I am saying is that this works as the kinetic term for your gauge field. And this is also called a Yang-Mills term, or Yang-Mills Lagrangian. Did I miss anything here? Probably not. Okay. So now we started with some action that looked like this. Then from here, we replaced the partial derivatives to covariant derivatives and introduced a gauge field. And to this thing, we added we are now adding a Yang-Mills action that only depends on A, and it's defined by this. So this is nothing but the spacetime integral of this. So you take d4x with some coupling constant in the front. So we will discuss the implications of the coupling constants and the Feynman diagrams in our next lecture. But for now, we want to flesh out the structure of the theory itself. Okay. So now we have a classical action where we have kinetic terms for our scalar and the kinetic term for our gauge field. Let's give it a name. Actually, let's not. And we want to integrate over all of the fields. So we have S phi A, S Yang-Mills A, and we are integrating over both phi and A. Okay. So now this is our quantum theory that we are interested in. Okay. Now let's take a closer look at this integration. The most troubling part about this integration is that most of the fields, all of these integrations, so these are integrations over the space of fields, right? Which are some large infinite dimensional space. Okay. Now, so this A comes from, again, some space of gauge fields. The most problematic part about this integration is that most of these integrand, no, that doesn't make sense. What I will say is that this integrand does not depend on most of the fields inside this space of fields. Now let me make it a bit more precise. Suppose you are doing a two-dimensional integration. Okay. Your coordinates are x and y, and you are doing some integration where you have dx, dy, and you are integrating some function of f of x and f of y. Now, it may happen that somehow you ended up with an integration where the integrand does not depend on y at all. Okay, so you just have dx, dy, and just f of x. So this is the kind of situation that I am talking about. So here, this integrand does not depend on half of the coordinates that you're integrating over. So that's what I mean when I say that this integrand doesn't depend on most of the gauge fields in here. So I mean it in the same sense as this f doesn't depend on half of the coordinates. Okay, why is that a problem? Well, so even in here, you can see that, so what is this integration? You have an integration over y that has nothing to do with anything else. And then you have an integration over x, which may be fine. This is definitely not fine. You're, okay, assuming you're integrating from minus infinity to plus infinity. So this is an integration that contains no information, just an infinite integration over an infinite dimensional space. The result is obviously infinity, which is, and there's nothing you can do about this, right? I mean, there's no physics that you can say that can take care of this. Because this is completely decoupled from the rest. Whatever physics you have is going on in here. I mean, not literally here. This is just a two-dimensional finite integration. But I mean that the analogous situation in here. Now, okay, so why do I say that most of this integrand does not depend on most of the A's? Well, so let's imagine that this space is the space of all gauge fields. Obviously, this is a matter of imagination. So let's imagine that this is the space of all gauge fields. Okay. Pick a particular gauge field. Let's say I pick A mu. Now I can do a gauge transformation, right? So a gauge transformation changes my A to something else. So we know that A mu goes to U, A mu, U dagger. I have already forgotten what it was. Minus IG something. Probably something like this. Okay. This is the new gauge field, right? And so this gauge field, this new gauge field may be here. Maybe this is my A mu prime. I can do another gauge transformation. Then I will get another gauge field, A mu double prime. Okay. So the point is, for each U, starting from this A, for each U, I have a new gauge field. So how many U's do I have? Well, what are U's? So U's are space-time dependent n by n unitary matrix. In other words, I can say that a U is a function from my space-time, let's say R4, to the unitary group, right? So for each point of my space-time, I have n by n unitary matrix. So how many such functions do I have? Well, I have a lot of them, right? Because in general, even if you just have a scalar function or R4, you have infinitely many of them. Because a function can continuously vary at different places, right? And here it's not even a scalar function, it's an n by n matrix valued function. So basically, Ux consists of many individual functions, U1, 1x, U1, 2x, dot, U1, nx, UN, 1x, and so on. Now, these functions are not all independent because it is still unitary. So the determinant of this thing has to be 1. Or rather, the dagger of this thing has to be its inverse. So you get some equation. So there are some constraints on these functions, but most of these functions are independent. We get a few constraints. So a lot of functions. So meaning that starting from an A, there are many A's that are related by a gauge transformation. And we know that this action is invariant under a gauge transformation. So you can choose the coordinates in your space of gauge fields carefully. So what you can do is that take any point and then draw out the subspace of your space of gauge fields that are related by gauge transformation. Meaning that if you start from here and you do a gauge transformation, you will land on another point in this line. If you do another gauge transformations, you will still be on this line, and so on and so forth. You do an inverse gauge
Gauge orbit.
transformations, you'll
Gauge
That's right.
orbit.
Yes. So for any point, you can define such a subspace. And yeah, as has already been pointed out, that this object is called a gauge orbit. If you know what an orbit is, then this will make sense. Gauge orbit. Yeah, I don't have to say anything more. But the point is that the defining property of this subspace over gauge field is that any 2 point on this subspace can be related by a gauge transformation. Okay. And of course, you can do this starting from any point. So this point will lie in a different orbit, and so on and so forth. And every point will lie in some orbit, right? Because starting from any point, you can draw an orbit. So in this way, you have basically, so this drawing of these things, it is equivalent to the drawing of the vertical lines in this XY plane, right? Because in that silly integration that I wrote down earlier, dx dy f of x, this f of x does not depend on y. So you can take any y and you can translate y to y plus epsilon, and this integrand does not change. So in this case, you can start from any point and you can translate y, and that gives you a vertical line. And starting from any point, you have a vertical line. So here you have a group of translations under which your integrand is invariant. And using that invariance, you can draw these lines. You can stratify your space into orbits of that symmetry transformation. And you can do the same here as well in the space of gauge fields. So in this sense, these two situations are similar. That here, your integrand does not depend on a lot of the coordinates. And here, your integrand does not depend on a lot of the gauge fields. So the problem that we ran into here, that we can choose coordinates so that we separate the coordinates that this depends on and the coordinates that it doesn't depend on, which we have already done here, right? We have x on which affects our integrand, and we have y, which doesn't do anything. We can do the same here. So imagine that we have separated our integration over A into 2 parts. One which affects the integrand and the other which doesn't. And the part that doesn't, the orbits will basically look like the space of all such maps, right? Because if you start from here, then for each such map, there is another point on this line. So this line basically looks like the space of these maps, which is huge. So similarly, so as we did here, so we separated this integration into a part that is an integration over the orbit of translation. So it gives you the size of this line times something else, something that we may hope to be able to compute. The same situation arises here. There's an integration over, let me call it B, and then an integration over the remaining stuff, let me call it A prime, and then whatever we had. And this B never appears inside this integrand. And this integration, here the integration was over a line because here the symmetry was translation. This integration is over the space of all such maps, which is a gigantic space. So this is an infinity many times. I mean, it's a very large infinity. It's not like an infinity of a real number.
It's divergent.
I mean, yeah, obviously, but it's not even just mildly divergent, it's terribly divergent. More importantly, So when we have a gauge symmetry, our idea about the system is that any 2 points on the gauge orbit describe the same physical setup. So if you have 2 fields, phi and a mu, and then you do a gauge transformation so that they become phi prime and a mu prime, these 2 things are physically the same. Now, why we say that? Because there will be no local measurement that you can do, or there will be no local observable that you can compute the expectation value of, or you can measure, that will be able to distinguish between 2 different kinds of field configurations. Basically, the gauge transformations are completely invisible from the point of view of the observables of the theory. What I'm saying is not very rigorous, but I'm just saying that this is the intuition. And in practice, what you will find, so the concrete statement is that any observable that is not gauge invariant will have a vanishing correlation function. But the ultimate physical interpretation is this, that any field configuration is related by gauge transformation should be treated as physically the same field configuration. So an integration over a gauge orbit, you are basically counting the same field configuration a bunch of times. And we should not do that to begin with, right? Because it's the same thing. Why are we integrating over the same thing over and over again? So what we wrote down here, it was too naive. We shouldn't have written down an integration over the space of all gauge field configurations. We should only write down the integration over the physically distinct gauge field configurations. So what we mean by that is that in this orbit, pick one field from this orbit. From this orbit, pick one field. From here, pick one. From here, pick one. And similarly, from each of these orbits, pick one gauge field configurations. So then you have some line like this. And you should only integrate over this line. You should not integrate over this full space, just over this line, because this line contains physically distinct field configurations. Okay. Now, okay, so which point do you pick from each orbit? So there are obviously many points, and as we said, they're all physically equivalent. So here, instead of this, I could have picked this. Right? So I could have drawn other lines. I could have drawn these lines. So as long as a line intersects each orbit only once, that is a perfectly valid line to draw. And then you can say, this is the line over which you should do the integration. But what if it turns out that the integration over this line is different from the integration over this line? Well, that would be problematic because, again, we are saying that these 2 points are the same. So it shouldn't matter whether I pick this point or this point. So all of these that I'm saying, you have to incorporate these things into this integration, because this integration we just kind of just wrote down. We just added a field and said that, okay, integrate over this field. But this was too naive, as we just explained. So we have to very precisely give a prescription for how to integrate over the fields A, so that we're only integrating over these lines. And furthermore, the result of the integration should not depend on which line we pick. We should be able to pick any line, do the integration, and we should end up with the same answer. So that is the story of gauge fixing. Gauge fixing means that in this orbit, which are called gauge orbits, you fix 1 point. So from each orbit, you fix 1 point. So basically, so you're drawing this line. So drawing this line that are transverse to the gauge orbits is called gauge fixing. And we have to do this in a way that our path integration does not depend on our choice of the gauge that we chose. choosing a gauge means choosing one point from each orbit. Okay. This will take some time, and I don't want to rush this too much. So I think it's better if I start this topic in the next class. See, I still have a couple of minutes today, so okay. So let me just summarize what we did today, and maybe I can move to answering some questions. So to recap, so what we did, okay, so this is next class. So what we did is that start with a theory with global symmetry, G, where G is some Lie group. And then promote partial derivatives to covariant derivatives, which are written as follows. Here, before we do this, we should say that in here we have fields phi transforming in representation rho of the Lie algebra of G. And then you modify the partial derivative using that representation. Okay. Then add Yang-Mills action. So this is the F² term, trace F². And this doesn't depend on which representation you have. Doesn't depend on rho. I mean, recall that there was a rho in the trace. But as I said, that this will always be proportional to the metric of your Lie algebra, which doesn't know anything about any representation. The only place where this shows up is in the proportionality constant, and the overall proportionality constant doesn't really matter. And there is some canonical proportionality constant that people usually choose. And then, so up to this, everything is classical. So classical era ends. And then we have to do the gauge fixing. And by this, what we mean is that we have to give a prescription for how to integrate. So this means how to integrate over the gauge fields in a way that we do not integrate over the same field configurations multiple times, and that we do the integration in a way that the integration doesn't depend on our choice of representatives of gauge orbits. Okay, so these are the primary steps. And as you can see that this step, well, as in the example I talked about the scalar field, but this statement is more general. You can start with any theory that has a global symmetry with G. So it can be scalar field theory, it can have fields with any other spin. As long as it has the global G symmetry, it has some kind of term with some derivatives. And the prescription is the same. Simply replace the derivative with this. And the only place where you have to worry about what kind of fields you have in this theory is in the choice of the representation. Your fields in the theory will transform in some representation of your symmetry group, and you just have to pick this representation to be the same. We will see some examples. We will write down some actions with some fermions and so on. Okay, so in the next class, we will discuss gauge fixing, and there will be some time left, hopefully, and in that time we will maybe draw some Feynman diagrams. And if even more time is left, then we will maybe discuss something called the asymptotic freedom in QCD, which is beyond the course anyway, because it will rely on renormalization, but it's fun stuff, so we can talk a little bit about it. Okay, so now if there are any questions, yeah, I can answer.